To understand gravity, where should we begin? Let's begin where Isaac Newton began, with the apple. Everyone has heard the story of Newton and the apple. Here's the cartoon version. Isaac Newton is sitting under an apple tree, and an apple falls and hits him on the head. And so Newton discovers gravity. That's an absurd story, of course. Nobody ever discovered gravity. It's a basic fact of everyday life. So, what was Newton's discovery, and what did the apple have to do with it? There are several versions of the story. Doubtless, Newton told it many times in many ways. Today's version was recorded by the French philosopher Voltaire, who heard it from Newton's niece. In the autumn of 1665, Newton has received his degree from Cambridge and will later return to Cambridge as a fellow and then as a professor. But there is an outbreak of bubonic plague in England, so the university is closed. So Newton is spending a few months in his hometown of Woolsthorpe in Lincolnshire. While walking in his mother's orchard, he chances to see an apple fall. And he thinks, the earth is exerting a force on the apple. We call it gravity. And this force can reach out pretty far. High up in the air or on a mountaintop, the apple still falls. So maybe this force could reach even farther out into space. Maybe the gravitational pull of the Earth could extend all the way to the moon. Maybe this is the force that steers the moon in its orbit, bending its path continually toward the Earth. So Newton tries out some calculations. He compares accelerations of the falling apple and the orbiting moon. He makes a reasonable guess about how gravity might get weaker with distance, and the math comes out pretty closely. The idea works. This is the start of a 20-year journey of discovery for Newton. And along the way, he invents entire new branches of mathematics and physics. To support his idea about gravity, he establishes a new science of force and motion, the part of physics we call mechanics. We will say much more about Newton's mechanics in Lecture 4 and beyond. The point of the story here is Newton's profound insight that the same laws govern motion both on Earth and in the heavens, that the same force that causes the apple to fall also steers the moon in its orbital path. Both the apple and the moon are examples of the same thing, gravity in action. This is a big step forward in the whole history of human thought, and it is also a key aspect of our course. Gravity is about both phenomena near at hand at the human scale, everyday and intuitive, and phenomena far off at an astronomical scale, exotic and surprising. Gravity is a fundamental link between the commonplace and the cosmic. So let me show you something pretty cosmic. This is a supercomputer simulation of two colliding galaxies created at the National Center for Supercomputing Applications. It simulates the physics of one of the most stupendous events of the universe, the collision of two spiral galaxies like our own. Each galaxy contains 100 billion stars, plus clouds of gas and dust and so on. And in the collision, the disk structure of each galaxy is completely disrupted. Huge arms of stars and gas are flung out into space, and eventually the crowded nuclei of the galaxies merge together, and the two galaxies form a larger elliptical galaxy. The whole process might take 2 billion years. This is not just an imaginary scenario. Galaxies are in the process of colliding all over the universe. We can see hundreds of examples. In a telescope, of course, we only see a snapshot in time for each collision. It's the computer that lets us understand the long, drawn-out process in its entirety. Our own Milky Way galaxy has probably undergone collisions with smaller neighbor galaxies and is predicted to collide with its nearest large neighbor, the galaxy M31 in Andromeda, a few billion years from now. The most important force shaping such titanic events is gravity. Thus, from the simple fall of an apple toward the Earth to the complex dance of huge gas clouds and billions of stars in a galaxy collision, we are looking at the same kind of physics, gravitational physics. And it is hard to imagine two phenomena that look more unalike. Yet if we look deeper, we will see that there are deep similarities, common characteristics of the gravitational force. So here is the first essential characteristic of gravity. Gravity is a long-range force. That was Newton's original idea. The gravitational pull of the Earth extends to the apple and even out to the moon. The sun's gravity steers the planets in their orbits. Gravity holds each galaxy together, and it even reaches from one galaxy to another, hundreds of thousands of light years. Gravity does get weaker with distance, but there is no upper limit to its range. By the way, the weightless condition that astronauts experience while they are orbiting the Earth is not because they are so far from the Earth that they are beyond the reach of its gravity. No place in the universe is actually beyond that reach. And in fact, the strength of the Earth's gravity at the distance of the International Space Station is almost 90% of its strength on the ground. The real reason that astronauts experience zero gravity while in orbit around the Earth is something much more subtle and interesting, as Einstein will reveal in Lecture 14. The astronauts experience their zero gravity in their spacecraft because both the astronauts and the spacecraft are falling together through space. Now here's the second essential characteristic of gravity. Gravitational forces are almost unimaginably weak. Now at first, that seems a strange thing to say. The apple accelerates toward the Earth at about 10 meters per second per second. Physicists call this acceleration 1g, that's a little g, and it only takes about half a second for the apple to fall to the ground from my hand. Suppose we drop it from higher up? Well, if the apple falls freely for just 3 seconds, it is moving as fast as a car on a freeway. That is a respectable acceleration. But that acceleration is the result of the gravitational pull of the entire Earth, all 6 billion trillion tons of it. All that mass acting together only produces an acceleration of 1g. But what about the galaxy collision? Surely those forces are immense. Well, yes and no. It is easy to be fooled by the scale of our computer simulation. Remember, the collision takes billions of years to happen. If we calculate the acceleration of one galaxy due to the gravity of the other, we only get 1/trillionth of g. Later in the course, we will see situations where gravity is immensely strong, collapsed stars like neutron stars, and black holes. These situations always involve a stupendous amount of matter crammed into a tiny volume. The fact that so much mass is needed to create such strong gravity only reinforces the main lesson. Despite its overwhelming importance in the universe, gravity is actually a weak force. Now, here's the third essential characteristic of gravity. Gravity is an attractive force. Given any two objects, the force of gravity pulls them toward each other. Now, this does not mean that they will actually get closer together. For example, the Earth's gravity bends the moon's path toward the Earth, but this just keeps the moon curving in its orbit. The attraction of gravity is mutual. That is, as the apple is attracted to the Earth is also attracted to the apple. But the acceleration of the Earth is undetectably small. And gravity works the same way for anything. There are no objects that are repelled from the Earth and fall up. This is true as well in the collision of the two galaxies. Those streamers of stars and gas that are flung out into space are not actually repelled. It is simply that the gravitational attraction of one galaxy is stronger in some places, the near side of the other galaxy, and weaker in other places, the far side of the other galaxy. And this difference in gravitational pull is called the tidal effect. And this is what actually disrupts the structure of each galaxy. As we will see, this difference is also responsible for the ocean tides on Earth and extreme volcanoes on one of the moons of Jupiter. Fourth, and finally, gravity is a universal force. Newton realized that the Earth attracts not just the apple, but also the moon. In fact, each part of the Earth attracts each part of the apple and each part of the moon. Newton called this the law of universal gravitation. Every two pieces of matter in the universe attract each other. We will see this force at work in the collision of two galaxies. There are hundreds of billions of stars in the galaxies, not to mention gas clouds and so forth. Each star exerts a gravitational attraction on the other star. This is the essential reason why the interaction is so complex. This is why you need a powerful supercomputer to begin to understand the details. Thus, gravitation is a long-range but very weak universal attraction between masses. And that makes it unique among the basic forces of nature. So, what are the basic forces of nature? In fact, what do we mean by a force? Well, these days, a physicist will use the term force to mean any interaction among particles. This interaction might cause changes in motion, that's Newton's original idea of force, but an interaction might also produce changes in the particles themselves. For example, a process by which an unstable particle decays into other particles would be due to some fundamental force. We know of four fundamental forces which appear to account for everything we see. And two of them are very short-range forces, the strong and weak nuclear forces. And two of them are long-range forces, the electromagnetic and gravitational forces. The strong nuclear force affects only some kinds of particles, protons, neutrons, mesons, and so on. In fact, it is a force between quarks, the basic constituents of those particles. And it is very short range, extending over only about 10 to the minus 15th meters. That's a millionth of a billionth of a meter. And it is the strong nuclear force that holds the quarks together within the particles and also holds the atomic nuclei together. So in that sense, it does affect the motions of those particles. It keeps them from moving apart. The weak nuclear force affects more kinds of particles, not only things made of quarks, but also electrons and neutrinos. It is roughly 1,000,000 times weaker than the strong force, and its range is only 1,000th as far, 10 to the minus 18 meters. Thus, we see its effects only in particle transformations. The weak nuclear force, for example, is responsible for some kinds of radioactivity. This brings us to the electromagnetic force. This involves two closely related phenomena, electric forces and magnetic forces. The electric force is a force between static electric charges. Objects can have positive or negative charge, zero is also possible, and like charges repel each other, while opposite charges attract. The magnetic force affects magnets and wires carrying electric current, electromagnets. And about 200 years ago, physicists realized that both were different aspects of the same thing. They're interactions among electric charges, whether at rest or moving. So, like gravity, the electromagnetic force is long range. Its strength does diminish with distance, but it can exert some influence even very far away. And the electromagnetic force is moderately strong. It's 100 times weaker than the strong nuclear force, but it's thousands of times stronger than the weak nuclear force. And it only affects particles that have electric charge. It affects quarks and electrons, but it leaves neutrinos alone. Electromagnetic forces are almost as familiar as the force of gravity, and they are responsible for a vast variety of phenomena. These are the forces that steer a compass needle or produce static cling in clothing. Electromagnetic forces keep the electrons in an atom bound to the nucleus. They're responsible for the short-range forces between molecules that hold solid objects together. light itself is an electromagnetic phenomenon as well. It's a moving disturbance of electric and magnetic fields. Now, we do know about some relations between these forces. For example, we know that there is an underlying connection between the weak nuclear force and the electromagnetic force. They are both aspects of the same underlying electro-weak interaction between particles. But where does gravity fit in with the other forces? Gravity is different. Unlike the two nuclear forces, it is long range. It can act over great distances. And unlike the electromagnetic force, it is always attractive. And unlike any of the other forces, it is universal. It affects all kinds of particles equally. And it is also weaker to a fantastic degree than any of the other forces. So let's compare gravity to the electromagnetic force. As we said, electric charges of the same sign repel each other. So two positively charged protons repel each other. Two negatively charged electrons repel each other. Of course, the two electrons also attract each other by their mutual gravitation. So which is stronger, the electric repulsion or gravitational attraction? Well, let's let Fg stand for the gravitational attraction of two electrons, and Fe stand for their electric repulsion. What is the ratio of Fg to Fe? It turns out, conveniently, that this ratio is the same no matter how far apart the electrons are. Both forces are weaker when you get far away. But the ratio is an astonishingly small number. The ratio, Fg divided by Fe, is 2.4 times 10 to the minus 43rd. Note that we are using so-called scientific notation to express really big or small numbers, and we will need this quite often in our discussion of gravity. So here's what we mean in this case. You start with 2.4, and then you shift the decimal place 43 places to the left. That's what 10 to the minus 43rd means. So you end up with a number which is 0.0000, 42 zeros in all, then 24. So the ratio of gravitational forces to electric forces is fantastically small. Gravity is more than 1,000,000 trillion times weaker than electromagnetism. So how could such a weak force be of any significance? How could it make any difference? Well, gravity does matter. And indeed, for really huge things in the universe, it matters most of all. And here's why. Electromagnetic forces are much stronger than gravity, but those forces tend to cancel out. So take two pennies. In each one, there are huge positive and negative charges, protons in the atomic nuclei and electrons around them. So the protons in each penny would exert a giant repelling force on each other. How giant? The force is about the weight of a mountain range. And the electrons would repel too. But the protons in one penny also attract the electrons in the other, and vice versa. So the net electric force between the pennies, when you add it all up, is 0. The gravitational forces are tiny, but they are always attractive. Gravitational attraction cannot cancel out. All masses attract each other gravitationally, and the more mass you have, the greater that attraction. And this means that for really big objects in the universe, gravity is by far the most important force. Let me explain this a bit further by asking a very simple question. Consider the solid bodies orbiting our sun, the planets and asteroids. What forces actually hold each of these bodies together? Basically, there are two job candidates here. For this particular job, there's candidate number one, the intermolecular forces, which are short-range forces that reach from one molecule to the next. They're weaker than the chemical bonding force that holds the atoms in the molecules. Now, even though these intermolecular forces reach less than 1/1000th of a meter, They are, in fact, due to the long-range electromagnetic force. So, to explain briefly, the total electric charge of each molecule is 0. But at any given moment, the positive and negative charges within the molecule are not exactly in the same places. And this means that two nearby molecules can experience a net residual attractive force. The second candidate for our job of holding things together is gravity, by which all parts of a body exert mutual attraction on each other. And this is a much longer range force, but as we've seen, it is very weak. So consider a small piece of rock. It is held together by intermolecular forces. Gravity is completely insignificant. And it is easy to see that this is true. If you create a thin crack all the way through the stone, a gap too wide for the intermolecular forces to reach across, but no obstacle for gravity, then the rock does not still hold together. It comes easily apart. Now, if you want to vaporize the rock and disperse its molecules all over the universe, you will need to put in a good deal of energy. A physicist might call this the binding energy of the rock, though disintegration energy might seem more apt. Some of the energy that you put in will go into turning the solid rock material into vapor, that is, into overcoming the intermolecular forces. And some of the energy will go into dispersing the molecules, that is, to overcoming any gravitational attraction that they have for each other. And in the case of the rock, essentially 100% of the binding energy is due to the intermolecular forces, and almost none is due to gravity. Now consider the planet Mars. Suppose you want to vaporize Mars and disperse its molecules all over the universe. How is the binding energy apportioned? That is, which would take more energy, the vaporizing part or the dispersing part? Well, it would take a huge amount of energy to vaporize a whole planet. Yes, but in fact it would take several times as much energy to overcome gravitational attraction and disperse the molecules all over the universe. The binding energy of Mars is almost entirely due to gravity. Gravity is the main force that holds together a planet. So, which bodies in our solar system are held together mostly by intermolecular forces, and which ones mostly by gravity? There is an easy way to tell. Take a look at this image of the asteroid 433 Eros. The number, by the way, indicates the order of discovery of the asteroid. 433 Eros was the 433rd asteroid discovered. It's a long, angled, irregular piece of rock about 30 kilometers long. Some have likened its shape to a banana. Now look at asteroid 21 Lutetia. It's quite a bit larger, more than 120 kilometers in its longest dimension. Its shape is still quite irregular, but it is more globular than 433 Eros. Now take a look at one of the largest asteroids, 4 Vesta. Its largest diameter is 570 kilometers, 5 times larger than 21 Lutetia. Its shape is quite rounded, but not quite spherical. And finally, here is the Earth's moon, 3,500 kilometers in diameter, which is about 6 times wider than Vesta, and its shape is essentially a sphere. And all of the larger worlds of the solar system, the main planets, the dwarf planets like Ceres and Pluto, all the larger moons, are nearly perfect spheres, sometimes slightly fatter around the equator because of rotation, but essentially spherical. So why this progression of shape from irregular to spherical? The reason is gravity. An object that is held together by short-range intermolecular forces does not really care what overall shape it is in. That is, each part is linked only to parts immediately adjacent, and there is no tendency to smooth out irregularities. Even if gravity plays some role in holding the pieces together, it is very weak. For instance, take a look at the asteroid 4179 Tutatis, which passed just 1.5 million kilometers from the Earth in 2004. Toutatis is just 4.5 kilometers long. In fact, it may actually be formed of two distinct fragments, just barely held together end to end by gravity. But its irregular shape is mostly due to intermolecular forces. But a solid body held together by gravity, by a long-range attractive force between all masses, will tend to pull itself into a spherical shape. Every piece of the body is attracted to every other, even to pieces on the other side. And a sphere is the shape that minimizes the distances between all the pieces. And the more massive the body, the stronger this tendency will be. But gravity is so weak that a solid body has to be many hundreds or even 1,000 kilometers across before this sphere-making proclivity of gravity will win out. So this progression of shape that we see among the solid bodies in the solar system, from irregular smaller bodies to nearly spherical larger ones, rather neatly illustrates the essential characteristics of the force of gravity. Gravity is weak for small-scale objects, but on the largest scales, it is the most important force. Thus, in astrophysics, the physics of astronomical bodies, planets, stars, galaxies, and so on, and their interactions with each other, gravity is the most important force shaping the structure and motions of the universe. And in cosmology, the physics of the universe as a whole, gravity is king. Isaac Newton discovered that gravity is a long-range, extremely weak, universal attraction between masses. And we will spend the first half of our course exploring the meaning of Newtonian gravity and how that force shapes our world, from planetary orbits around the sun to ocean tides to the complex dance of many-body motion. But Newton's theory does not really explain what gravity is. To go deeper, to begin to comprehend what gravity is, required a genius equal to Newton himself, Albert Einstein. Einstein was one of the greatest scientists of all time, and his theory of gravity, the general theory of relativity, is his greatest work of genius. Newton's insight was that a commonplace phenomenon, the fall of the apple, could represent the same physics as the motions of the heavens, from the orbits of the moon to the collisions of galaxies. Einstein's insight was that to really understand the fall of the apple, we must be prepared to understand an extraordinary idea. What we call gravity is actually a distortion, a curvature of time and space. This involves a revolutionary change in the way we think about motion, matter, and the whole universe. And it leads to some of the most mind-bending phenomena of contemporary physics. And that will be our subject for the second half of the course. The subject of gravitation is extremely beautiful. It's a subject that I have been in love with since my earliest days as a physicist. My first published research paper was on black hole physics. As a theorist, a chalk and blackboard kind of physicist, I love the elegant theories, the lovely way that the basic concepts work together. Einstein said that the theories of physics are essentially creative, like works of art. And so gravitational physics includes the masterworks of some of the greatest artists of all time. But as I've prepared these lectures, I've also been struck by something else. Gravitational physics has also involved some of the most wonderful experiments and observations in the history of science. Laboratory measurements of great delicacy and astronomical observations of extraordinary precision. And these are elegant and beautiful too, and they are the real foundation for our understanding of the universe. And beyond all that, there is beauty in the way that gravity shapes the world, the pure curve of a planet's orbit, the intricate structure of Saturn's rings, the billion-year splash of stars as one galaxy collides with another. Powerful telescopes on Earth and in space have shown us images of immense splendor, nebulae, stellar nurseries, exploding stars, galaxies, and it is gravity that shapes them all. Most of all, I find the subject of gravity marvelous because of that astonishing connection between here at home and way out there, between the fall of the apple and the path of the moon, between everyday experience and those mind-bending theories of physics. To truly understand one, we must also understand the other, and this profound link will be our touchstone throughout our course. We will begin with the here at home, with some observations about motion and force, about falling bodies and flying projectiles made 4 centuries ago by Galileo Galilei. These observations will perhaps seem elementary, but from the simplest of facts, sometimes the most profound of consequences follow. Again and again throughout our course, we will see how the discoveries of Galileo will be the starting point not only for Newton's understanding of motion and gravity, but for Einstein's as well. Everything that follows begins with Galileo.